Hello, this video is about the reaction mechanisms of carbonyls. So specifically we're going to be looking at ketones or aldehydes here. We're not considering the reactions of some of the other groups that have a carbonyl in them for now. We'll cover that later on. So first thing, whenever you get an organic molecule and you're trying to do a reaction mechanism, make sure you put in your dipoles and your lone pairs. So here's a carbonyl compound. I've drawn propanone as a fairly standard one. A couple of lone pairs on the oxygen, delta negative, and the crucial for all carbonyls, this carbon, the central carbon, is delta positive. And what that means is that carbonyls react with nucleophiles. So a nucleus lover, so something which has a lone pair or a negative charge. I'm going to show you a sort of generic version, Nu with a negative charge, and that covers whatever they throw at you. So I'm going to give a couple of the most obvious and typical examples later on in this video, but if in an exam question you are given an ion or a molecule that has a lone pair and therefore could act as a nucleophile, then there's a chance it could react in this way. So if you want to pause and just have a think what might happen, that's great. Hopefully you've looked at this and you know that reaction mechanisms are all about bringing opposite charges together. So the lone pair of electrons are attracted to the delta positive carbon, and so we're going to show this as a curly arrow. Now the curly arrow always starts at the negative, it always starts at the pair of electrons, and it is the movement of a pair of electrons. You've got to be really accurate here. Start it at the lone pair and take it accurately to the carbon atom. What you can think of this is like a dative covalent bond. It's an atom that has a lone pair of electrons donating it to another atom. There is a problem. This carbon will now have 5 bonds and the carbon can't have 5 bonds. So what happens is that the oxygen, which is delta negative and is pulling the electrons away, is in fact able to take one whole pair of the electrons that were in this double bond to itself. So you have to draw an arrow that starts in the middle of the bond, because it's showing the electrons from that bond, and draw it to the oxygen atom. So what is then going to happen is that you first of all put in everything that has not changed. So the easiest thing to do here, my central carbon, the CH3 to the right, the CH3 to the left. And now let's think about what has changed. Well, there was a double bond to oxygen. There is now a single bond. And instead of having 2 lone pairs, you've now got 3 lone pairs. You have, of course, now got a bond down to whatever the nucleophile was. Now, all of these reactions are going to take place in an aqueous environment. So that means that there's a water molecule nearby. Sometimes they will take place in acidic conditions, still aqueous, where you will have direct access to an H+. But if there isn't the stating that there is an H+, if you draw in the water molecule, lone pair from this oxygen that's now an ion is attracted to the delta positive hydrogen. And as a new bond starts to form between the oxygen and the hydrogen, very similar to what happened in this step, from the electrons from the bond to the atom like that. And again, the things are unchanged first. So that is what's going to happen for these reactions. There are 2 steps. One, the nucleophile forming a bond to the carbon, and at the same time the double bond breaking, and the second, protonating, adding an H to the oxygen here. So if you look, you've turned a carbonyl into an alcohol, and you've also added something else on here. Now, there will be a spectator ion present. This nucleophile, if it's an ion, if it's an anion, there has to be, say, a sodium or a lithium, something that is present and will then balance out the charges. So perhaps you added Nu minus with an Na plus, and then you'll have still the Na plus, so the byproduct is sodium hydroxide. Right, try and give you a specific example. There are two typical examples. The first one is the cyanide ion. I've drawn it really quite, well, large to try and make sure you can see what's going on here. You have the carbon with 3 bonds to the nitrogen, and then instead of having a 4th bond somewhere, we've got a lone pair on the carbon and a negative charge. So that's showing that the carbon has gained an electron from somewhere. So this is, therefore, with the lone pair, the carbon atom here is able to be a nucleophile, and it's going to be at the carbon rather than the nitrogen, because the carbon would typically have 4 bonds. As ever, you're going to add in your dipoles, and the carbon's delta positive. Please pause and try and see if you can figure out what will happen yourself. Okay, hopefully you did that. You know it's going to be curly arrows. Start them at the lone pair on the carbon, bring it directly into the atom, and you then have the the double bond from the carbon to the oxygen. One of them, doesn't matter if the bottom or the top, have that breaking, and both of the electrons, the pair of electrons, going onto the oxygen. So we're going to draw in everything that hasn't changed, and of course the carbon hydrogen single bonds down here. If you were lucky, you will get a very simple molecule, but they could draw an absolutely massive long chain of hydrogen and carbon. It won't change, it's just there as distraction. The interest, the reaction, is happening at the functional group. So, single bond to the hydrogen there. We know there's now a single bond to oxygen, and that's going to have a negative charge. And so that's what we've got here. As above, we then need to protonate. I said before it will either be a water molecule or it could be an H+. Now you can sometimes get away with drawing the arrow from the negative charge, but it's preferred that you draw it from a lone pair. I'll just make that really obvious there. And yes, if you do it wrong and you try and fix it like that, as long as it's not too convoluted, you should still get away with things. So apologies for this slight curve here. I'm going to twist the molecule round because I want to make it all fit in. So here is my CH3, CH2, which matches this. We have now the OH bond, we have a hydrogen there, and then we have added the C with triple bond to the nitrogen. This is something that's very useful in organic chemistry, because what we've done is added an extra carbon to our molecule. So this is one of these useful things to know for synthetic techniques, because you can increase the carbon chain by 1. The conditions for this, as I mentioned earlier, you can't just have the anion on its own. So you would have, say, sodium cyanide. You could get away with lithium cyanide. And I've used sulfuric acid as the source of the H+. Okay. The other typical reagent that you will get at this point is something called NaBH4. Now, in year 12 you should have come across BH3, which has the boron with its 3 outer electrons forming 3 covalent bonds with hydrogen. Hopefully you remember when you looked at this in year 12. 3 bonding pairs, no lone pairs, equal repulsion, 120 degrees. And in year 12, you no doubt said, hang on, boron doesn't have a full outer shell, how can this be stable? And you were kind of onto something. It is not stable as BH3 on its own. But what we can get is this interesting chemical, NaBH4. And the boron would have its 3 outer electrons. The 3 hydrogens that you had previously would form their standard covalent bonds, but then we would have this extra hydrogen here, And you can see I've drawn this final electron with a different symbol, because what's happened is that is the electron that you could associate with the sodium. So you end up with an ionic compound that has a complex anion, where you've got 4 hydrogens bonded to the boron, so this will be 109.5 degrees and it's going to be tetrahedral, and then you have the sodium ion. Now this chemical here is something that we're not allowed to play with in school because it's very, very, very reactive, and it's a source of a hydride ion, which is H minus, because basically this is going to come away leaving you with BH3. So it's BH4 minus splitting into BH3 and H minus, and this is something that just goes against everything that you have learned before, because you're used to seeing H plus, and that's where you've really got to be careful with this. Everything that you've done, you will think, oh yeah, this is the hydrogen, it's H plus. No, be really careful. It's a hydride, it's H minus, and this is the reactive thing, because we've given hydrogen 2 electrons, but it doesn't know what to do with them, and it is going to go out and it's going to react with the first thing it encounters. And if that was a year 13 student in a classroom, then it would react with you. Please don't play with this at home. So let's say we pick a carbonyl. Let's do ethanol. Please try drawing ethanol, pausing the video and adding the dipoles and figuring out what will happen yourselves. Okay, hopefully you did that. If not, oh well, please try next time. Delta negative on the oxygen, delta positive on the carbon. We know nucleophilic attack is going to come here. Here is my hydride ion. Again, lone pair of electrons from the nucleophile attracted to the carbon, and we have this bond here breaking. And so drawing in everything that hasn't changed, the carbon with 3 hydrogens. To the left, the hydrogen that was present. Now, instead of the double bond, we have a single bond to oxygen, and the new bond that we've formed is a hydrogen there. The next step, this is a 2-step process, excuse me, would be the addition of water or acid, and that would allow us, as before, to protonate. And the final step here, just to fill in all of the missing atoms, is to show what we've done. And we have therefore turned ethanol into ethanol. The type of reaction that we've done here is a reduction, because you've previously come across ethanol being oxidized to ethanol. Well, this is reversing the process. So NaBH4 you need to add to your list of chemicals that you know, and it's a reducing agent, because here we have taken the carbon which has 2 bonds to oxygen and now it only has 1. I'm not doing it with oxidation numbers just now because it's about mechanisms, but this is a reduction, and so if you need to, in a question, take a carbonyl and turn it into an alcohol, NaBH4 is what you would need. Bear in mind that you would have a byproduct of BH3. Thank you very much.